Alright, so this is our first sample problem for the topic on static stress analysis. And recall that our goal right here is to do computations regarding combined stresses. Now, this problem is taken from the textbook by Peitel, actually Peitel and Kisalas. The textbook title is Strength of Materials, and this is example sample problem 8.2. The problem says that to reduce interference, a link in a machine is designed so that its cross-sectional area in the center of section is reduced by 1/2. So here is our link, our mechanical link, and right here at the middle portion, it is, the cross-sectional area is reduced as compared to the section at ends. The thickness of the link is 50 mm. So this is the thickness, and the distance. Um, we have this distance 40 mm and 40 mm, and we are asked to determine the maximum and minimum values of the normal stress at this section right here. Okay, so here's our loading. This is the centroid at this portion, but of course, if we are going to take the stresses at this middle portion, then the centroid would be something right here. Okay, so this is an example of combined stresses. Okay, so for the solution, then the first step is let's draw the FBD, the free body diagram, and let's try to draw this free body diagram in 3D. Okay, and we will draw the section. Okay, so here is our section. So I'm making a cut right here, and this will be our mechanical part. And right here, this is the point of loading. So this is P, and let's write, this is 40 mm, this is 40 mm, and I think we should have drawn this a little wider because this is 50 mm. Okay, so because we made a cut, then that means that we are going to expose the external forces, the internal forces. So we have an internal force and axial force, right, going this way, and we'll also have bending moments. Why? Because if this is our force P, and right here is gonna be our internal forces, right? This is the centroid of this section. But right here, the centroid is the centroidal axis is somewhere along here. So that means that we will have this distance. So this distance right here, we will have this half of 40. This is 20 mm. Okay, so if this is our force P right here, so to make this mechanical link in equilibrium, then of course there's going to be an opposite force going this way, And since they have a moment arm or something like an eccentric distance, then if with respect to this, let's say this is our point of let's say center of moment, then this will cause a counterclockwise rotation. So in order to maintain equilibrium, there must be um, bending moment right here. Okay, so sometimes I use simple P, or sometimes I just use N. Just take note that this is or I'm referring to internal forces. Okay, so here's our figure 1, let's say, and this is our figure 2. So now let's uh, let's calculate the internal forces. Okay, so if we take summation of forces at x, let's say this is our x-axis and then this is our y. Now in this three-dimensional, this is x, this is y, and this will be our z axis. So summation of forces along x, then we see right here that the n is just simply equal to um, n is just equal to p. And by the way, I think we we forget some given right here. So given that p is equal to 40 kN. Okay, so let's write here p is equal to 40 kN. So if we take summation of forces along x, then we see that n is just simply equal to p is equal to 40 kN. And if we take summation of moment at the section right here, if we take moment at the section, what we obtain is that the moment, the internal forces or the internal bending moment is just equal to 40 kN times the moment arm of 20 mm. This is kN, this is mm. Then this is just, I think this is just the same as 800 Newton meter. Okay, so now we have the internal forces. Then what we need is the geometric properties, such as the area, and then the internal the moment of inertia. Okay, so solving now for the geometric properties at the section. Okay, so for the area, this is the cross-sectional area right here. This is just 50 times 40. So 50 times 40, this is just equal to 2000 mm squared. And for the moment of inertia, this is rectangular, and here is our axis of rotation. This will be 1/2 of base times h cubed. Okay, so 1/2, and what's our base? Our base, this base is 50, right? Okay, so right here, this is 50 mm times the height. So from this point to that point, what's going to be the height? Because we're taking moment of inertia at the centroid. So this is 40 cubed. And if you do the computation, what we get is 266.67 times 10 to the 3 mm cube. And another geometric property that we need is the value of the distance from the centroid at the section to the outermost fiber. This is just simply 20 mm, right? Because this is 40 and this is half, so this is 20 mm. Okay, so now let's drawing the stresses. stresses or stress blocks. Okay, so if here's our section right here, right? So if here's our section and we have stresses, and so we have actual stress. Sorry, this should be intention, and we also have the bending stress. Right. Okay, so here's our stresses. This is actual stress, and this is the bending stress. This is MC over I. This is N over A. Okay, so now let's solve for the actual stress. I think this is step number 5. Solving now for the stresses. Okay, so for the actual stress, this is just N all over A. So let's not worry about the sign if it's positive or negative. Let's just solve for the values. So N is 40 kilonewtons. This is 40,000 newtons divided by the area, the cross-sectional area. This is 2,000. So 2,000 mm squared, and this is 20 megapascals. And for the bending stress, we have this equation mc all over I. So m is this is 800. Okay, let's just write 800,000 Newton mm. Okay, so this is Newton mm times the I retain this millimeter because our unit for C and for the section modulus, for the moment of inertia, it's in mm. So this is 800,000 Newton mm times the distance from the neutral axis to the outermost fiber. This is 20 mm divided by our moment of inertia times 10 to the 3 cube, and what we get is 60 megapascals. Okay, so let's now drawing now the stress blocks. So if this is our section, now the critical stress block is just simply right here for the outermost fiber. Then we can also check this one, the middle portion, if you want. And let's label this is A, stress block A, this is stress block B, and this is stress block C. Okay, so this is our orientation. Then if we zoom this in, say this is our A, this is our B, and this is our C. Okay, so what are the stresses at stress block A? Okay, so we have tension right here. So we have let's say this is the normal or the actual stress, and in terms of bending moment, so this is compression right here. Okay, so this is Q sub B. This is the bending moment for stress block A. And for stress block B, we don't have, since this is the neutral axis, then we don't have the bending stress. but we only have this axial stress. For the C, we also have axial stress, except that for the bending stress, if this is in compression, so this one is in tension. Okay, so they have the same direction right here. So therefore, for stress block A, this is just, or we'll write it here. So for stress block A, this is negative P, or negative N all over A, plus MC all over I. So this is just, what is this? This is 20 megapascals. 20 megapascals, but this is negative, all right, plus the value of the bending stress, this is 60 megapascal. So this, we have 40 megapascal for the stress block at A. Now for the stress block at B, we only have axial stress. So this is just sorry, I guess this should be positive and this one is negative. Right? Or let me write it again. This is positive minus MCL over I. So what we get here is negative 40 megapascals. And for the stress block at B, this is just simply the actual stress, which is 20 megapascal. And for the stress block at C, this is, so we have the same direction, and this is N all over A plus MC all over I. This is 20 plus 60, so we get 80 megapascals. All right, so let's review our solution. And what we did first is to draw the free body diagram so that we can determine the internal forces. So once we have the internal forces by just applying the equilibrium equations, then the next step is to solve for the geometric properties if it's not given. We have to solve for A, we have to solve for the moment of inertia, and then we draw the stresses because this is a combined stress. Although this may not be necessary, but I mean in some textbooks they may not express this in terms of three-dimensional, and because sometimes it's really hard to draw the three-dimensional stresses, especially if this is round or circular section. So but it's a good way to practice, though. At least we can visualize, because if there's going to be a lot more internal forces, like if there's torsion and transverse shear, then yeah, I think this can help us visualize the problem. Okay, so once you have all that, then we solve for the value, for the magnitude of this bending stress and the actual stress. Then we draw these stress blocks so that we can visualize if we do plus or we do minus. And then we solve the values. All right, so I guess that's enough, and we'll do our next sample problem. All right, here's our second sample problem for this topic on static stress analysis. And this one is taken from the textbook by Beer et al. And the title of the textbook is Mechanics of Materials, and this is example 8.01. Okay, so the problem says that two forces are applied as shown at the end A of bar AB. So we have this bar AB right here, and it's fixed right here. And we have this force, 18 kilonewton force and 15 kilonewton force. So this bar AB, right? We have this bar AB right here. Sorry, by the way, this is the bar AB, and then this is the cylinder. So bar AB is welded to a cylinder member BD of radius 20 mm. So the radius of this cylinder is 20 mm, and we have this bar that's being welded at this cylinder. Knowing that the distance from A to the axis of the member is 50 mm, so from this point to that point, this is 50 mm, and assuming that all stresses remain below the proportional limit of the material, determine the following. So first, the normal and shearing stresses at point K. We have here the stress block right here. So the point K, this is it. Um, the normal and shearing stresses at point K of the transverse section of member BD located at a distance B is equal to 60. So from this point to that point, this is 60 mm from the end. And for letter B, the principal axis and principal stresses, we'll skip this one, and also letter C, we'll also skip this because these are topics on stress transformations. Okay, so my approach in this is I'd like to draw this the other way around because the textbook it uses it cut a section right here, but it um, but it consider only this portion. Although either way, you can actually work on that. But for me, I think I'd rather cut the portion right here, and then I want to maintain this body because I have the forces right here. Although, as I've said, you can actually work. You can work either way, depending um, upon which is more convenient to you. Okay, so for the first step, so let me redraw this. So I'm going to, if this is, say this is our X, then this is our Y, right? And this our Z. So I'm going to rotate this, the XZ plane, I'm going to rotate this 90 degrees. So what I'll get is something like this. Or let's write our line label first. Drawing the FBD. Okay, so something like this. Okay, and this is X, this is my Y, and this will be my Z axis. And for the forces, we have this 18 kilonewtons, and we also have this 15 kilonewtons right here. Okay, so the next is this is the cut section right here. Right, so this is the cut section. It's right here. Okay, so because of this cut section, then we have to expose the internal forces. Okay, so because we have this, we have two forces right here. So let's just expose all the 6 forces, right? So we can have actual force, right? That's along the X direction, and we can also have shear force that's along the Y direction. Basically, it's the forces along the Y, and we just name that V sub Y because so that we can track if it is if it is shear, or if it's moment, or if it's torsion. And right here we have also forces, and let's say this is V Z, And if we have forces, then we also have moments right here. So the direction, this is just random. If we compute and it happened that it's negative, then it means that it's the other direction. So this is moment along the y, and this is torsion. Okay, so the moment along the x, that's actually torsion. And right here we have the moment along the z-axis. Okay, so now let's apply the equilibrium equation. Okay, so if we take summation of forces x is 0, so what we get is we can solve for this px, so any forces along the x. So we have this p sub x and we have this 15 kilonewtons, right? So px minus 15 is equal to 0. Then if we rearrange, px would be equal to 15 kilonewtons. Okay, next is to take summation of forces along the y is equal to 0. So the forces along the y are this Vy, this internal force, Vy, that's downward, and we have this 18 kilonewton external force. So 18 minus Vy is just simply Vy is equal to 18. 18 kilonewtons. Okay, so the next step is to solve for summation of forces along z is equal to 0. So we don't have any forces along the z. So it means that it's just 0. That the next step is to take summation of moment along x is equal to 0. Okay, so any forces that causes rotation along the x-axis, what are those forces? Well, we have this torque right here, right? So we have this torque, and we have this force and a moment arm right here. This is 50. This moment arm right here. All right, this is 50 mm, right? And right here, this is 60 mm. Okay, so 50, so 18 times 50. Okay, and you would notice that this one produces like something like, let's say this is a counterclockwise, but this one will produce a clockwise. All right, so that means that what we get a torque value that's positive. So torque is just simply 18 kilonewton times the moment arm of 50 mm, and this is 18 times 50. This is 900 newton meter. Okay, the next step is to take the summation of moment, let's say along y is equal to 0. So summation of moment along y is equal to 0. What are those forces or moments? We have this m sub y, and let's say this is a clockwise rotation. Then what are the other force, or what are or is there any other force that causes rotations along y? Yes, there is. That's the 15 kN force. Because we have this moment arm, then it will produce rotation along the y-axis. So this is clockwise. This one also produces clockwise. So we get a value of negative, right? So that means that instead of having a clockwise, we should rather have a counterclockwise rotation. Okay, anyway, let's write it here for now. My is equal to negative 15 kilonewton. Negative because supposedly it should be on the left hand side. They have the same sign, but I write this at the right hand side, so this is negative 15 times 50 mm, and what I get is negative 750 newton meter. And for the summation of moment along the z axis, it's equal to 0. So mz, okay, rotation along the z axis. So we have this mz internal force and this 18 kilonewton times the moment arm of 60. Right, so you would notice that they have the same direction, so we'll get a negative value of mz. This is negative 18 times 60 mm. So this is 1080 newton meter. This is negative. Alright, so I guess I'll continue our discussion in the next video.